My name's Colin Baskin. Now, I'm the unit coordinator for this particular subject and also teaching the distance cohort of students, of which you are all obviously members. So it's a 12-week course, and it's kind of structured around 12 hours per week, but that's 144 hours of structured learning. Now, at this stage, can I just ask you to mute your microphones and invite you at any stage when you've got a question just to unmute your microphone and jump in. Okay, it's really that simple. We're here for about a 50-minute conversation, and I do want to hear from you. I don't want to be the one doing all the talking. All right, so let's get cracking. What we've got here is, it's a really good place to start the course. We've got a Year 3 students' representation of science. Now, a representation is really just a mental model, and there's a lot of research done on mental models and what they represent. They're hypothetical, imaginary situations, and maybe the student has experienced this kind of science. It's been first postulated by the American philosopher Charles Sanders Peirce back in 1896. So mental models are, quite an old technology. And anyone who's doing the multiliteracy subject, of course, will come across the fabulous work done by Ludwig Wittgenstein in 1922, where he did his picture model of language. Every word is simply a picture, and we associate things with that picture, and based on that, we've got language. So it's an interesting point. Now, I'm going to ask you, what do you see when you look closely at this picture? Maybe Melissa, would you like to tell us a little bit about what you see? No, not Melissa. Anyone like to jump in and tell us a little bit about what you see? All right, we're all the strong, silent type. Interesting. Okay, so what I'll talk about then, if I have a look at this, we've got people. Now, clearly, if we look up here, and I'll just use the computer mouse here just to indicate, we've got actually someone in a white coat. And what I really want to point out here is the representation. Here we've got the science experiments. We've got the tubes, we've got the Bunsen burners, we've got obviously the student. And the student is working from, if we look at this image. So there is a notion of experimentation here. There's a notion of replication. So the student is trying to replicate and produce clearly some evidence. And when we look up here, the scientist is sitting above this in the background, supervising in his white or her white coat. So what we've got here is a very, very clinical version of science. Now, just for an introduction and overview, this first week we talk about science. It's an education, and it's critical in developing members of society, making evidence-based decisions, and it's particularly in an age where science is arguing a lot about it and with itself. For instance, we look at issues like global warming. Does it actually exist? And this topic explores the theoretical frameworks that underpin science education across the nation. It's using the Australian curriculum framework. And we point out that scientists and science is always constantly evolving. Now, science was first coined as a term back in the 19th century, so it's pretty recent. And when we look at Mesopotamia, 3,500 BC, mathematics was born in Egypt around about the same time. Iraq was one of the leading scientific nations back in that era. We've got earth sciences, astronomy borrowed from the Greeks, Plato, Aristotle. Aristotle actually came up with 354 biological classifications for animals. So science is ancient. Leonardo da Vinci was an artist. Well, he became famous by drawing and dissecting anatomical specimens. So the link between art and science is quite strong. And of course, we look at science and we can see that some of the great philosophers of the world, Galileo, he didn't invent the microscope, but he certainly challenged the church at the time to look beyond the earth as God's only creation. So we can have a look at those sorts of concepts and see how science and the church have constantly been locked head to head in debates around ethics around the world. Which brings us on to some of the other points that we're going to make at the moment. Our learning outcomes, clearly the aim of this topic is to list where students connect with science. to describe the ways in which scientific understandings can be effectively enhanced, and also to explain some different types of learning theories. And I'll just draw a caution around that third learning outcome there, because a lot of the theory that your textbook looks at is actually quite outdated. So computers are a relatively new phenomenon, and a lot of the behaviourists, cognitivists, and even some of the social constructivists, I mean, Lev Vygotsky was writing around 1921, so some of these theories are quite outdated and they need to be brought into the modern era. When we look at the key terms in science, clearly the science itself, it's knowledge created from activities and thinking about people over time. It's how our understanding changes. We're also going to look at the term contextualising. Science means different things to different people, hence we've got perspectives. And we're going to talk a little bit today about Indigenous perspectives. Learning theories, they've been researched and formulated. They guide our thinking about learning. And finally, some really interesting misconceptions, and some of these are talked about by Professor Goodrum in that introductory video where he talks in week 1 about the Australian curriculum perspective. And he talks about the needs of students at each phase of learning and how a curriculum framework needs to address that. Now, we'll pick that up more in week 2. But we're also talking about learning for understanding versus learning purely for scientific knowledge. And this is the challenge of science, to make itself relevant to the world. He talks about the new curriculum, which became popular or implemented around about 2012, and its more traditional focus on biology, earth and science and space sciences, hence our focus in this subject on those 3 sciences. And he also talks about it as an exciting era in science teaching. Our week 1 learning activity starts off with a really interesting discussion between Frank Bowden and Ashley May, and they set the scene for this week's discussion. And at one stage, Frank Bowden points out that about 40% of Americans don't believe in evolution. They actually believe the world, despite the argument of science, is they believe the world is only 10,000 years old. And at that point, on the 7th day, of course, in creationist science, God rested and the world had been created. Now, if we look in public education, I've given you a little bit of a map there just to show how divided science is, even at the educational level in the United States. There are 2 particular states, Louisiana and Tennessee, and public schooling can actually opt out of teaching evolution and teach the creationist sciences instead. Frank Bowden also raises the issue of antibiotics, and this is a big one. I mean, in the world at the moment, we've got 5 base family groups of antibiotics. And in Africa, for instance, they're 100% ineffective. The body become immune. Across the Asia region, they're 96% ineffective. So we have a major problem, don't we? When we're looking at health and medicine, can science produce a solution? Well, earlier this year, late last year, science has actually come up with a solution. As our antibiotics fail and continue to fail, science have actually decided and invented a way to modify the human gene. So they modify one receptor gene. It actually now enables the body to digest and respond to antibiotics once again. Is that a solution? Well, who knows? Since that happened, or actually 4 years ago, an American company has taken out a legal patent on the human gene. So science, money, ethics, religion, this is a really interesting field. PISA, one of the topics we're asked to look at 2012-2015, because it's relevant to school performance. And we can see that there's an argument that Australian schools are slipping backwards relatively against OECD nations when we look at the PISA performance. That's a relevant point, but we are still above OECD averages. And our curriculum was only implemented in 2012, so our actual experience of PISA may take some time to change. And for those of you following the news today, of course, you may realise that it's International Women's Day. You may also realise that it's the day the NAPLAN results are released on the My School's webpage too. So if you're curious at all, go and see how your old school is doing. You were asked to have a go at one of these PISA 2012 question samples. And as you can see, it's quite a complex problem-solving activity. If you take the blue box and you navigate down to the problem-solving activity, you'll see that context is quite strong in these questions, even though it's about problem solving and it's about geography and distance and it's interrelated. There are multi-literacies at work. And if you haven't had a go at the task, please do, because this is the context in which the new Australian science curriculum is being taught. We are connecting very heavily to student context and students' situated learning. A couple of the activities we were asked to look at. And perhaps I think one of the most compelling is this one. Based on the video on the TED Talk with Bo Lotto and Amy O'Toole. And Bo asked the question, armed with two ideas: science is a way of being and experiments are basically a way of playing. He asked, can anyone become a science? And of course, a scientist. And then he looked, of course, at a group of 8 to 10-year-olds. And of course, they produced a peer-reviewed published paper. Now, I've actually put a link to that peer-reviewed paper in the subject website for anyone who wants to go and have a look. It's not compulsory for you to do that, but it gives you an indication of the untapped resources of science. In my own background, I've done a lot of work with Lego, and Lego, translated from the Danish, literally means play well. And one of the roles I've been fortunate to play is starting robotics competitions right through the Asia Pacific and right across Australia. And we've seen some amazing solutions. I've seen 10-year-old kids patenting nanotechnology fish that swim. The little nano baits are programmed to swim like particular types of bait to attract particular types of fish. When Arnold Schwarzenegger was governor of California, they had an incredible erosion problem on Santa Barbara Beach. So a group of 12-year-old kids said, we've got the solution, and they took out some PVC piping. They put some chains in the ground. The piping they put on rope, and they drilled holes in the pipe so that when it went out with the tide, it picked up the sand and distributed it. When it came in with the tide, it picked up the sand and redistributed it, so there was no beach erosion. That idea is now being used globally to resolve erosion issues. So when we look at science, what do we know about science? The key question here is, how can I find out? That is the key question. Brainstorm. A couple of ideas here. When you've looked at this, and again, David Attenborough. Everybody loves David Attenborough. It's like a grandfather. Marvel Comics, other comics, Superman, Marvel movies, time and space, books, everyday life, when rainfall, acid rain, a fascinating phenomenon. For anyone ever been caught in it, it does burn. Bread falling butter side down. Now you think, what the hell is that doing in there? But in fact, that's about surface tension. Why does butter stick more than bread? It's a really interesting scientific experiment. Drought, floods, cyclone tracking. Kids love that. And of course, the seasons. Anything we can build around the seasons. And families provide often explanations for science. I remember having an uncle who had a terrible problem with flatulence. He used to fart all the time. And as a kid, he was really, really cruel because he'd say, pull my finger. And of course, you pull the finger and he'd fart. And as a child, I actually believed that there was a connection there. And that was my uncle's explanation for it. A brilliant new book too, Julia Enders, writing about gut bacteria and the connection of the gut from everything to obesity and allergies to Alzheimer's. I mean, science is appearing everywhere. A wonderful app that I use, and I will encourage you to have a look at this, a phone app that I've downloaded, and particularly when we look at next term in chemical sciences, it's called Chemical Maze. And basically all you do is you enter the number or the name of a particular chemical in a food, and it tells you what happens. And I was really shocked the other day to discover that Diet Coke, actually the body converts Diet Coke, or one of the major ingredients in Diet Coke, into formaldehyde. In other words, you are pickling your own liver, which is a really interesting discovery related to that. Contextualizing. Every piece of science has a context. That helps us talk about it. And this is one of the things where we're starting to move on to our learning theories. The better we are at embedding science in a context, the more likely that we're actually going to give that science, I guess, some good explanation, some good airplay to young learners. Contexts give meaning. They relate to life experience. They can be regional. Okay? Every area has its own issues. We can weave science throughout the curriculum. It's about being curious, about asking that key question, why? Where do I go to find out? The doing component. Science has an everything. And again, teaching of science is only limited by your imagination. Now on this slide, Linda Pfeiffer shows that even the science, even Christmas has a science. And for anyone who's not familiar with the notion of using stations to teach, it basically involves setting up your classroom, in this case, with 5 different points, and maybe north, east, south, west, with a table in the middle. And each of those represents a station. And at each station, the students are going around doing a hands-on touch and feel, real-life experience of the scientific concept. And these can be really simple. Christmas tree decorations, reflection, light, colour, refraction, a sleigh, friction. What kind of sleighs work best on which surfaces? Design one. Wrapping paper, 3D shapes, lengths, candles, wax and water. Christmas lights, looking at electronic circuits, simple systems, and then opening up discussions about complex systems, maybe even computers. When a light goes on, it's because there's a simple system connection. When a computer goes on, it's about zeros and ones. So you can do all kinds of different things. Everything has a science. Your textbook, Gregson, talks about learning theories. Now, you could become quite bogged down in these, but what we really need is a working understanding of them. And the key components here is that all learning theories have a history, and they have families they belong to. For instance, Skinner experimented with rats. Watson, Bandura, was a social learner. He used a Bobo doll, and he watched children as they punched the Bobo doll and it fell to the ground and bounced back up. And he watched children and designed learning tasks based on social observation. Cognitivism, we've got people like Piaget, Bruner, Gagné. Cognitivism is about actually the individual learner constructing their own knowledge. Really interesting point here is how does the learner know the knowledge they're constructing is right? And this is a really interesting point. Abraham Maslow was a humanist. In 1923, he published his treatise on humanism and self-actualization. In other words, Maslow says we learn to satisfy our needs. Social constructivism. Vygotsky, Freire, and Michel Foucault, an interesting group of people. Vygotsky wrote in 1921, he was a Russian, interesting philosophies on freeing up learning. Freire wrote the emancipatory curriculum, so he tried to free learning from institutions. And Foucault was a sadomasochist, really interesting Frenchman who wrote a lot about schools and schooling and how that was really a form of social control. So in these learning theories, we have a lot of territory to cover and a lot of scope. Your textbook treats them quite lightly, but I think it treats them appropriately for our course. Just beware that when we do use these theories, we will jump in and out of different theories depending on the role and the task of learning that we've got going. Your task actually asked you to look at the similarities and differences. And I've listed the 3 there, cognitive theories, behaviourism and constructivism. And there's one I've put on the right-hand side up here. A man by the name of George Siemens published a new learning theory about networked learning called connectivism. And we'll talk a little bit more about that as the year progresses. But what it does, it introduces technology. It introduces the World Wide Web. It introduces distributed learning. And it talks about how these 3 other theories can coexist within a broader networked learning environment. So we can look at the common areas. They do overlap. They all are geared towards creating changes in learners. So for instance, cognitive theorists would get people to think about their learning Behaviourists would measure the success of that in learning outcomes and evaluate the actual behaviours and learning principles that emerged. Constructivists would say, go out there and do it. Okay, I do, you watch. You do, you tell me what you're doing. You do, you demonstrate. And then you go out and do again in the real world. So learning theories, they do interrelate and they do come together. And your task is to think about and do some theorising yourself about where that might happen. Bloom's taxonomy is raised as part of this week's course as well. Now, Bloom's taxonomy is, it's just a taxonomical way of structuring some of our learning theories, and a taxonomy is basically just a list. So what we've got is behaviourism, cognitivism, constructivism. They're three broad learning theories, and they're most often used, and they have been used a lot in teacher talk and in design of learning environments. But they're developed at a time, and again, I stress this. Okay, question? No? Okay, continue. Please feel free to jump in, and I will hear you and I will be able to respond. But these theories were produced at a time when learning was not impacted through technology. So we now need a new theory and a new curriculum, 2012, we've got it, where it's going to bring science into this new model of learning. So after over the last 20 years, technology has reorganised how we live, how we communicate and how we learn. And a couple of the key things here, the half-life of knowledge is shrinking. In 2005, it was believed that knowledge had an 18-month lifespan. Believe it or not, that's down to 9 months now by 2016. Many learners move into a variety of different and usually unrelated fields in their lives. We need to develop a style of learning that enables that movement. We can't just be a scientist and nothing else. Informal learning is a huge part. Dr. Google. We all know about Dr. Google. Learning, it's a continual process and it lasts for a lifetime. And I know it sounds like a life sentence, you're going to be a lifelong learner, but actually it's a positive thing. Technology is altering and rewiring our brains. People like Mark Prensky began this study back in 2002, 2005, showing how neuroplasticity is rewiring our brain. So parts of, some functions, some cognitive functions that Piaget would have wrote about, we now rely on our computers to perform. Now, most of you carry quite a powerful computer in your pocket, your mobile phone. If you have a diary, if you have notifications from Facebook, if you have all of that, you are already outsourcing some key cognitive processes to the computer world. And it's not only cognitive processes. A study done in America recently showed that the shoulder movement of boys aged 14 to 21 has reduced in one generation by 25%. In other words, the rotor cuff movements in the shoulder. And this is because we sit hunched over our computers, tapping on keyboards. There's a very strong scientific correlation. And many of the processes previously handled by learning theories can now be offloaded or supported by technology, and computer games is a big one there. Computer games is about serious learning. It's about behaviouristic learning. Knowing how and knowing what is being supplemented by knowing where. And if we look at Bloom's taxonomy, we can see that it's an important framework for teachers. Okay, it starts in the middle with 6 basic concepts, and it asks us to work out. We can ask students, for instance, to engage in a comprehension exercise number 2. They can do this through the processes of paraphrasing, restating, matching, or even drawing. They can illustrate their comprehension by drawing a picture or looking at a cartoon or a series of cartoons and interpreting it. And some of the tasks they can do, some of the demonstrated behaviours, recording, drama, cartoon, story. They can build a model. They can draw implications from ideas. So Bloom's taxonomy asks us to start with a process. Number 1 is get knowledge. Number 2, build comprehension. Number 3, learn how to apply it. Okay? And so on and so on. Right up to stage number 6. do have a close look at your textbook and what they talk about with Bloom's, because Bloom's is quite embedded in the 2012 curriculum framework. A couple of things that happened here in the share activity 9. Think about it in the Gregson text. Asked you to modify a plan for one group of learners. And at this point, we introduced the notion of embedding Indigenous science perspectives, and I actually put a link to a page by Sam, and I'll try and bring it onto your screen so you can actually see it, by Joe Sambono. And it's a really interesting presentation because, and I encourage you to have a really good look on slides 20 to 28, because Joe goes on to talk about, he's a curriculum development officer with DEET here in Queensland, and he goes on to talk about Indigenous perspectives, and he actually analyses the curriculum. So this little slideshow is very useful, not just for this week's material, but for next week's as well. And when it comes up with slide number 20, which I'm hoping it will, there we go. And he gives a couple of examples. What does a lesson look like that contains an Aboriginal and Torres Strait Islander history or culture? And he gives a couple of quick examples. So he gives a Year 10 example here. Responding to global issues, the curriculum area he's talking about, under ethics and human action as part of the science curriculum. Students will discuss Aboriginal peoples and Torres Strait Island peoples' knowledge about environmental management and climate change. A really interesting topic and an interesting perspective. He goes on again and gives a little bit of a lesson summary. And again, reduces it down to scientific principles, the global issue of carbon dioxide and how humans are working to reduce it. Another one he looks at, for instance, a Year 4 project, materials and their purpose, how Indigenous peoples of the world use natural materials. Now, Joe is a very experienced educator, but certainly gives us some really, really good insights there into how to deal and how to actually modify a lesson for a group of learners. Gregson in your textbook goes on to talk about the gifted and talented, learning disabilities, ESL, girls, boys, and the subtle nuances and difference of teaching to these different student groups. Now, I'm going through this fairly quickly. This is an introductory week, and it's very much about wetting the whistle, about getting you into the resources and materials, getting you confident moving around the subject website in ways that are actually going to enable you to enjoy the course and feel confident working around it. And I'll take some questions a little bit later too on the assessment, because I know some of you do have some concerns, and that's also part of the reason why I'm going through the course a little bit, the introduction at least, fairly quickly. The final part of week 1 talks about the nature of science and introduces a character by the name of Randy Bell. Now, he talks about the nature of science, and the question says, basically asks you to think about what is important, what do we need to include, what enables us to build a curriculum around scientific inquiry, so that we actually are talking about why science is science. What is scientific about this? And he comes up with this little diagram on page 2 of his article. You'll find it online if you haven't already done so. And the characteristics, he's got 7 characteristics he refers to. Tentativeness, that we can't simply go in there and teach science as knowledge. We've actually got to teach it as inquiry. So in other words, the learner has got to ask some questions about it. Second point, empirical evidence. Really, really important to base judgments about science on empiricism. Now, some of you know about Karl Popper, testability, verifiability, all of these principles of Popperism and science. Randy Bell talks about that too. Empirical evidence is important in reaching conclusions in a scientific curriculum. Observation and inference. The philosophers used to call this reason and reasoning. But we actually observe science in action, and we draw inferences from what we see. Scientific laws and theories, the origin of the species. It's a really interesting debate. The famous story about Charles Darwin, he was out insect hunting. He had the most amazing insect collection as a young child. And he found 3 new insects this particular day. And what he'd normally do is run home with an insect in each hand. But he realised he was out of hands. So what he did is he picked up one of the insects, put it in his mouth, put the other 2 in his hands, and he ran home and pinned them to his pinboard. So this is the kind of excitement that science can generate. And of course, Darwin went on to create the origin of the species and the theory of evolution. And the sad fact is there, he held on to that theory. He didn't release it for a few years. The reason being, his wife was a very, very strong religious person. And he actually believed that his theory would be the end of religion. He believed it would be the end of his marriage. And he was so reluctant to share it. And he did it with a very, very heavy conscience, ultimately because he had to. Scientific method is the 5th point raised by Randy Bell. You've got to explore something in a structured and generalisable way. In other words, it's got to be capable of being repeated. Creativity. Science must be, above all things, creative. Otherwise, it becomes reductionism. Reductionism is a negative science. Okay, we don't want to reduce science to simple principles. We want to expand it into an exciting universe. And objectivity and subjectivity both are required, which is, seemingly a contradiction. But if we don't doubt something, then how can we possibly set up an objective process of testing it? So Randy Bell talks about these principles of science and therefore argues that science has a context. The teaching of science has a very, very structured 7-part context. And this takes us back the full circle to our very first presentation, the PowerPoint in the Australian curriculum, little video snippet at the very start of this week's work. It talks about the context of science. Explicit instruction is important too, says Bell. Students will learn what we want them to learn about the nature of society only when they're taught it in a purposive manner. Context is very important, and the sorts of things that we talk about here as we go back to the video, the TED Talk, previous in the learning tasks, inquiry activities, socio-scientific issues, episodes from the history of science, all of these things can be used effectively as the context. And as Linda Pfeiffer demonstrated, even Christmas is a context. And of course, Randy Bell's final point, process skills. Teaching students to observe, measure, infer, classify and predict as part of a normal science inquiry. I do urge you to have a read of these articles, to develop some of your own questions around science and the teaching of science, because this is what you will communicate to your learners. These are the skills and the excitement levels that will make science teaching fun for you as a teacher as well. Misconceptions on closing. Cotton comes from sheep. It's a very common one. When things dissolve, they disappear. Of course, one of the principal laws of physics. Energy and matter doesn't change. It simply changes its form. It doesn't disappear. Mass and weight are the same thing. A really interesting experiment there. Dinosaurs and cavemen lived at the same time. A good one for the younger age groups. Sounds cannot travel through liquids and solids. I recently supervised a student, a pre-service teacher, who argued that he could project to his students and set up a science investigation using mobile phones and car keys. That he actually would send his car key electronic signal down through a mobile phone, which was stationed at the door of a car out in the car park. And it was a really fascinating scientific investigation. So I urge you to have a think about that one too. Mixing paints is the same as making colours or same as colours. And plants get food through their roots. So some really interesting misconceptions there to explore and to get going with science. Right. Now, at this point, I know there are 11 of you